Before we can talk about graph traversal algorithms, it's important to understand how graphs are represented in computer programs. We, as human beings or cats, can clearly see there are four nodes A, B, C, and D, and that A is connected to B and D and C, and B is connected to D. But how do we convey that to a computer? I'm Miss Paws, and you are watching part 1 of a two-part video on graph representations. In this video, we are going to focus on some of the relevant terminology that will be eventually important in understanding what type of graph representation we choose for our use cases. In part 2, we will talk about different types of representations. A simple graph is an unweighted, undirected graph containing no graph loops or multiple edges. A graph loop is what you see at node B, where B goes to B. Multiple edges is when there is more than one edge, like what you see from A to B, where there are two edges. While there are applications to graph loops and multiple edges, we will only be focusing on simple, weighted, or directed graphs for graph traversal. A connected graph is when a path exists between every pair of vertices in a graph. Here you can see this graph is not connected because there is no edge between A and any of the other vertices in a graph. The minimum number of edges for a connected graph is n-1 edges, where n is the number of vertices. The way we can reason about this is, imagine we have 4 vertices. Let's take vertex A. If we draw an edge to every other vertex, then the graph will be connected. There will be a path between every pair of vertices in a graph through A. A complete or fully connected graph is a simple, undirected graph in which every pair of distinct vertices is connected by a unique edge. You can see in the graph that all pairs of vertices are connected to each other. Now the formula for the number of edges for a complete graph is n-1 times n divided by 2, where n is the number of vertices. For example, in this graph we have 4 vertices, so that's 3 times 4 divided by 2 equals 6 edges, and there are indeed 6 edges. How did we get this formula? Well, let's start with our example. If there are 4 nodes, from A we can only have 3 edges, 1 to B, 1 to C, and 1 to D. Now let's go on to the next node, node B. We have already counted the edge between A and B, so now we have only 2 more edges, B to C and B to D. Then we repeat the process at C. We have already considered the edge between A and C and B and C, so now there's only 1 edge remaining, the edge between C and D. Then by the time we get to node D, we have counted all the edges. So that's 3 plus 2 plus 1 plus 0 number of edges. Put another way, if there are n number of vertices, we have n-1 plus n-2 plus n-3 plus so on and so forth all the way to plus 0 to obtain the total number of edges. You might recognize that there's a way to simplify the sum of this arithmetic sequence. The number you begin with times the number plus 1 divided by 2. So in our case, n-1 times n divided by 2. If you're not sure how I got this, stay tuned for a video on Gaussian summation. The important part for now, however, is just knowing this formula to calculate the total number of edges in a fully connected graph. A dense graph is when the number of edges is close to the maximum number of edges, or the n-1 times n divided by 2 edges we learned about. In our example graph, if we have 5 vertices, a fully complete graph would have 10 edges. Our graph has 9 edges since it's missing an edge between A and E. Since that's pretty close to the maximum number of edges a simple graph can have, this is an example of a dense graph. A sparse graph is when the number of edges is far from the maximum number of edges. In a connected graph, the minimum number of edges would be n-1. In our graph of 5 vertices, the minimum number of edges is 4. So if our graph, for example, would have 5 edges, it would be considered sparse. Sparse graphs can also be disconnected, so our graph of 3 edges is also an example of a sparse graph. Yes, this is a very hand-wavy, or should I say paw-wavy, definition, because sparsity and density depend on the context. When we are working with 5 vertices, the number of edges doesn't drastically differ between sparsity and density. But imagine we are working with graphs with hundreds of thousands of nodes. Then the number of edges truly make a difference. So this is all the theory I wanted to go over for today. The distinction between sparsity and density will inform what type of graph representation we want to use. Here's the terms we covered today: simple, connected, complete, fully connected, dense, sparse. Make sure to review these terms and stay tuned for our next video on graph representations in computer programs.